Hey, good morning, good afternoon, ladies and gentlemen. Today I'm gonna show this in this quick short webinar a project on the use of windscreen calculation method in FEKO. We're gonna look into an antenna, FM antenna, in the back screen of the vehicle. We're gonna import some CAD data or car components, the surface of the back screen, and we're gonna use some of the FEKO tools to construct the FM antenna, plus some extra heating grid structure that is always or 99% times present in an ordinary vehicle. All right, let's start. Let's get to the point. So I have this start model. This includes a car body. It's not a specific car body. To one, this may resemble BMW, but in general, this is nothing official. This is like a study model to practice the windscreen method, which is the topic of today's webinar. First of all, in the Home tab, we're gonna select this windscreen extension, which is normally not present in the menu above. So we press on the windscreen and we can see the windscreen tab appearing in the main top menu. Since we have the geometry already imported, we can give a short description of this. So geometry import 1, this is the car body. Geometry import 2 is the windscreen, or the rear screen, actually, back screen of the vehicle, and 3 is a sample antenna structure. We can rename these to using F2 button, car, rear screen, antenna. Oh, wait a second, something's not right here. Actually, we're not going to be using the antenna given here in the default dataset. We're going to construct our own so that we have so that we can get some experience in creation of the antennas on the rear screen of the vehicle on our own. All right, let's start with the materials or variables. And what we're going to need is some glass material. We need some foil in between. We're talking about a laminated glass in the back screen of the vehicle. So we're going to need glass plus some PVB foil. Let's get to the definition of the material variables. And these are epsilon for glass, which is 7.5. This is the approximate value at about 100 megahertz, as we're gonna be looking at FM antennas. Loss tangent of the glass. Then we're filling out the material data for the PVB foil, which is 3.1 the epsilon, and the loss tangent similar to the one of the glass, which is 0.05. Okay, so we get the material parameters. We need the thicknesses of the glass and the PVB. We're assuming 2.1 millimeters, and then the PVB is 0.8 millimeters. Okay, we got the variables. Let's construct a medium. Let's define, actually, not construct, but define a medium. First, the glass. And name it glass. Okay. Then the PVB. Okay. we're gonna use the feature of FEKO of the layered dielectric medium to construct the layered medium for the laminated glass structure. We go to the construct tab, media, layered dielectric. We're gonna start with the glass, which is h_glass thick. We have 3 layers because the PVB is in between. And again, so these are the thicknesses and the material. Okay, we didn't name the other one. Let's try to rename this now and see if it works. Okay, it worked. So we have that a layered dielectric medium made out of glass, PVB, and glass again, with the thicknesses given in the variable 3. As we have the layered structure, we go to the Windscreen tab. In here, we see a kind of workflow proposed that we just followed right now. So we defined the electric media, we made a layered stack out of it, and then we want to define a windscreen. So by default, our layered dielectric is selected. Okay, let's also name it so that we have a nice, clear model. This is laminated glass. Okay, we define a windscreen for the windscreen method out of this laminated glass. Offset L is a parameter defining the thickness of the whole window. In our case, this is the thickness of the laminated glass. We can then add all the thicknesses that are given to us by the laminated glass. Windscreen 1 is an okay name. In this way, we have all the materials necessary. What do we do now? We define our work surface to be this thing with the offset 0. Now we can see that our coordinate system, we have a new coordinate system that we're going to work at within this windscreen, or the rear screen actually, antenna. Let's exclude the antenna for now at least. Okay, what we're going to do now, we're going to draw some lines on the back screen of the vehicle to represent the heating structure and the antenna that we want to construct. Okay, we're gonna use the tool surface regular lines. This is a kind of local coordinate system, so we're gonna be using the local numbers. So horizontally, we're gonna have 15 heating grid lines, and we add this to our model, and then we're gonna have several vertical wires, namely for, okay, a mistake. We need to invert the axis, so we're gonna make it U-axis. In this way, we have a really nice heating grid, which is gonna be our scattering body for the antenna. These wires should definitely be included in the analysis because they are in the closest proximity to the antenna. And on top of that, the length of these wires is comparable to the wavelengths at some parts. So we definitely need to include this to have a proper result. Then we're gonna draw our antenna, which is our surface line tool here that we can use that helps us. And the antenna we draw as follows. we have the first line of the antenna, then the second line, the second small vertical line, and then we need another horizontal line below, so that the antenna is tuned to the right frequency. Okay. We also need some some extra wire to put the generator on, and we're gonna do this as follows. Hide the windscreen for a moment, and we're gonna draw a simple line from the construct tab, holding Ctrl plus Shift so that our mouse snaps to the closest vertex. We'll put this one here. Okay. We bring the windscreen back on. Let's put an infinite ground plane underneath our vehicle so that the ground effects are taken into account when analyzing the antenna pattern. Okay. And now, let's make the union of the parts at the end. And first of all, let's define how the layer of the glass is going to be solved. In the properties of the back screen face, we select the solution tab and we go to the windscreen method. And in here, we put on the windscreen 1 as the medium, and this is gonna be our reference element. So the screen is gonna be like a background for the antenna. Right now, what we can see that our plate got transparent, and this of course helps to visualize for us basically that the plate turned to a different solution method, namely the windscreen, and it of course resembles a windscreen. Let's union all the parts necessary. We union the antenna plus the vehicle. We also union the heating grid, and let's put the generator on the wire. Right click in the details tree, create port, wire ports. Let's put it here and make it a vertex port. We can reverse the polarity. Okay. In this way, okay, we have the port. Then let's put a voltage source on the port. And our frequency of operation is 100 megahertz. We would like, apart from the generator, we would like to see the far field pattern in not the whole sphere, but let's make it just the top hemisphere. This makes most sense, of course. Okay. We go back to the construction tab, and we still need to define the wires of our grid to be solved with the windscreen method. Offset A basically allows us to say, okay, where is the wire located in the window stack? In the way we designed this, our antennas and the heating structures is on the inside of the whole window. Therefore, we put value of 0 here. The same goes for these two wires. These wires. I have hidden the windscreen layer, and then the wires that are inside the windscreen should be solved using the windscreen method. Okay. I hope we are ready for the simulation. If anyone is curious, the length of the antenna is approximately 58, 59 centimeters. This is the value that I got optimized in some previous projects or some other work, and I just used the best number that I had in this quick webinar video. Okay, one more thing. Far field patterns are of course nice to see, but we would also like to see the currents on the antenna if our antenna actually has strong current distributions on it. Therefore, we again in the request tab we select currents, and in order to avoid lengthy computation, let's just calculate the segment currents on all segment current labels. Our request appeared in the configuration tab. We are ready to mesh the project, including the wire segment radius. We're gonna mesh our car. Okay, let's switch to mesh view. And right now we are able to see how our car was meshed. There are some triangle areas that are very much dense, the other ones are rather coarse. This all depends on the mesh settings that we use. In here we select standard, but in the advanced tab, these are some settings that I used for some previous projects, so of course this might not be optimal. We're gonna stick to what we have, and I have made the calculation of the project beforehand, so we're gonna jump straight to the results and we're gonna do some comparisons. Saying so, normally right now the calculation would have to be launched. We would have to wait for the results, which would be quite lengthy, as our car is 15,300 triangles big, and there are also some other components to calculate. I prepared results beforehand, so now we have the comfort to just have a look at the plots. And this way we jump to the post FEKO, our post processor. We have our car above an infinite ground plane, and I displayed here the current distributions on the back screen. Let's have a look here. We are looking at the currents on segments. Okay. I calculated 3 frequencies beforehand. We were talking about FM radio, so between 88 and 108 megahertz. This is what we're going to be looking at. At 108 megahertz, we have a hot wire, namely our antenna. So we have a really nice, good resonance at this frequency, and we can expect a nice performance of the antenna. Let's look at the other frequencies. Again, the same wire is in the red color. It's just some smaller pieces of this are red. Please keep in mind that the scale is automatic, so it's always better to lock the scale to some fixed values so that we can see the correct parts of the wires illuminated in the comparable scale. And 188 megahertz, again, the only wire that is red, that is hot, is our antenna. This basically tells us that our antenna is operating. It all looks very nice, but let's see the matching, if it's matched to some frequency. We got this one here. So I made yet another run including more frequency points, which gave us the smooth light blue curve that we're seeing in here. Also, we see the green and the red curves, which I was experimenting with. So I was making the antenna longer by 5.6 centimeters or shorter by 5.6 centimeters. The number comes from the division in the local grid that we were working at. So if you guys remember this place here, there was this gray dashed line grid with some local values, local numbers. The smallest division that I used in reality equaled 5.6 centimeters. So in this way, I was able to tune the antenna. As for the matching, in the middle of the band, we get about -5 dBs. Of course, this is not well matched antenna, but again, we might not be needing good matching for the FM antennas. We always get some signal levels. We have good electronics and amplifiers to get the signal to reasonable level and filter it out of the noise. Far field pattern. So as we can see, we have a pattern that is typical to the wire antenna pattern. Usually we would see a kind of a closed pattern that is closing itself out in here, but we can see the influence of the vehicle and of all of the every steel plate that is around our antenna. What we can see here actually is that the radiation pattern doesn't differ too much if we are even worsely matched than a light blue case. The same goes in the other plane. The radiation patterns are comparable. Of course, this is what we're looking at gain. If we looked at the realized gain, probably the case would be a bit different. So just to remind you guys, the realized gain, it includes the mismatch at the source. For 108 megahertz tuned antenna is actually worse in the radiation than the other two, because at 108 megahertz our matching for the blue curve is worse than the red and the green one. This is why the realized gain for the other antennas is better. And lastly, let's have a look at the 3D pattern. Is there a car? No, there's no car here. Let's perhaps put our car back into the picture and put the radiation pattern on. And in this way, we can see how the 3D distribution of radiation pattern comes about with our vehicle included. We can make our radiation pattern transparent so that we can see how this relates to our vehicle body. All right. Thank you all for attention. Thank you very much. I hope with this short video I could show the windscreen method, how it works, how to use it, and how the results look for this very simple FM antenna. Should you have any questions, feel free to drop me a mail. This can be found at the site. Thanks again for your attention and have a good evening. Goodbye. Thanks.